Welcome to Lesson 2 on Programming with C++. Today we about levels of programming language and syntax and semantics.
Today, the first thing that we are going to discuss is the different levels of programming language. In the last video, I already mentioned that computers only understand zeros and ones, right? So if you try to imagine the language that the computer understands, it looks something like this.
0, 1, 0, 1, 0.
This language is called machine language, and here 1 means on and 0 means off. So this is basically electrical signals. 1 means on and 0 means off. Think of this as the computer's heartbeat. Tiny electrical switches flipping on and off billions of times per second. So even a hello in machine language would look like this. But the main drawback for machine languages is that they are very hardware specific or very machine dependent. A particular machine language that is understood by a particular machine or a hardware may not be understandable for another machine or hardware. Another important thing is that this language is extremely hard for humans to understand. A program written in machine language for one computer may not work for another computer. So for that computer, another program should have to be written. And that also with zeros and ones. You can imagine how difficult that would be for humans to write new programs for every computer, and that also with only zeros and ones.
All right, one machine down, 20 more to go.
So after working with the machine language, with zeros and ones, the programmers realized that yes, they can make the computer do certain things with that language, but it is extremely painful for the programmers to write programs using zeros and ones, because you would go crazy finding out what each number means, what mistakes happen when you are writing programs, and how to fix those mistakes or bugs. So programmers decided to make a small bridge between humans and machines. And that's how assembly language was born. Assembly language came as a bridge between the zeros and ones that the computer understands and something that human can understand better. So it replaced those confusing zeros and ones with short, meaningful words called mnemonics. These are tiny instructions that human can remember, like MOV for moving a value into a register. If you remember, we talked about registers in the last video as well. Those registers are used for temporary storage within the central processing unit. So instead of memorizing long binary patterns, we now use simple instruction words. So assembly language is easier to read, easier to write, and it is easier to debug. But assembly language is still very close to the hardware. It is still very much machine dependent. Assembly written for Intel processors may not work for ARM processors. So it is better than machine language, but still not very portable. Now you might think we just discussed that computers only understand zeros and ones. Then how the computer is understanding this assembly language? That's where this assembler comes in. The assembler is a special program that reads assembly language, translates it into machine language. So it converts the mnemonics into binary instructions. You can think of the flow like this. The human writes this assembly language, which is human readable instructions. Now the assembler converts those instructions into binary machine code with zeros and ones. And then the computer executes those zeros and ones, that machine code. Now that we already know that writing in machine language is painful, and even assembly language still feels very close to the hardware, so humans asked a bigger question. What if computers learn to understand us instead of we trying to understand those machine level language with zeros and ones? That's how the high-level programming languages were born. High-level languages are designed for the ease of humans. They look like English words and simple math, and also contain clear logic. Languages like C, C++, Java, Python are all high-level programming languages. One of the biggest advantages here is you can write the same program and run it on different computers without changing the logic. Why? Because high-level programming languages are machine independent. So high-level languages can make programming easier, faster, less error prone, and more creative.
Compile, run. Yes, it worked here too.
No way. On the Mac as well?
It runs everywhere. This is awesome.
But we are still forgetting one problem. The computer still doesn't understand English. Even though we understand this high-level programming language, the computer still only understands machine language. So how does our high-level code actually run? Assembler was there to bridge the gap between assembly language and machine language. We have already seen that. Now comes another important tool that can convert high-level programming languages to assembly language. So we needed another bridge that can convert our high-level programming language that is easier for us to understand to convert to something that now the machine can understand better. So it can convert high-level programming languages into assembly language, and then there's the assembler to convert the assembly language to machine language. The name of this tool that can convert high-level programming language to assembly language is called compiler. A compiler is a special program. It reads high-level code, translates it into assembly, and then into the machine code.
And run.
Huh? What is all this? I don't get it.
Need a hand? I'll translate.
Whoa, zeros and ones? Now I understand.
Computers understand zeros and ones.
You don't see all this happening, but it happens every time you run a program. Now let's try to understand what happens behind the scenes every time we run a program. From your point of view, it feels simple. You write some code, you run a command, and you get the output that you desired. But inside the computer, a whole assembly line wakes up. Let's try to understand that. We start with the source code. This is the C++ file you write, full of English-like words, logic, and symbols. This is your idea written for humans. And when you type G++, then your filename.cpp, you are asking the system to begin translating your idea into something the computer can execute. Now, the first phase through which your program goes through is called pre-processing. The first stop is the preprocessor. Think of it as a text processor, not a translator. It handles the hash includes that you have at the top of your program, and later on you will see we will add something called hash define. It removes the comments that we add in our program, it expands the macros, and it does not understand logic and anything. It just prepares the text. Once this step is done, the code is cleaned and expanded. The next thing that comes is the compiler. This is where the real thinking happens. The compiler checks the syntax of the code that you have written. What is syntax? It is the grammar of the code that you have written using a particular programming language. We will talk more about syntax and semantics later in this video, but for now, just know that compiler checks the syntax, that is the grammar of the language. It verifies logic structure. It optimizes the code, and if there is any syntax error, this is where you will hear about it. The compiler will tell you that no, this line is not written as desired, or you are missing a semicolon there, you are missing that keyword that should be here in this line, something like that. After this step, your program is translated into assembly language, a low-level representation of your code. Now the assembler takes the assembly code and converts it into machine-level instructions. The output here is an object file. If you remember, when we were compiling our code using G++, we were creating an object file with the -o. Now when the object file is created, it has an extension .o. This object file is machine-level instructions for your computer. This machine code is incomplete. Why? Because your program may rely on standard libraries. I already told you a little about libraries. We will talk more about it in this video. It contains programs that are already written for you. Your program can also rely on external functions which are not there in your code, but you are using them because it is written somewhere else. it can also rely on other files. So we are not able to execute that right now. Now at this stage, the linker steps in. The linker's job is to combine your object file and attach the standard libraries. The standard libraries contain the codes that you have used in your program, and those are linked with your object file at this stage by the linker. And it also resolves missing references. Once linking is complete, you finally get an executable binary. This is the file that the operating system can run. So before this step, you had your object file that also contained machine language, but that was not executable because it has some missing areas or missing links. Now the linker stepped in and all those gaps were fulfilled with the standard library, the external files and all those things. Now the new file that is generated with all these new things is the executable binary file that can be used by the computer. After the linking step is complete, when you run the program, the loader takes over now. It loads the executable, the file that is generated, into the memory, and it links dynamic libraries. It prepares the program to run, and at this point everything is ready, and the next step is CPU execution. Now I use the term dynamic libraries, and you might wonder what is that. Dynamic libraries are shared pieces of code that programs use while they are running, and all the programs will use them no matter what. They are very common operations that are needed for all the programs, like opening a file or printing a text on the screen, handling keyboard or mouse input, doing math operations, all these things. On Windows, you can see these dynamic libraries as .dll files, or on Linux you will see them as .so files. On Mac OS they are .dylib files. So all these files are dynamic libraries for each types of operating systems, and they are common for all the programs that you will run. So instead of writing them separately in your program, the loader just links these libraries into your program whenever you run your code. So the final step comes here, the CPU execution. The CPU executes the machine instructions one step at a time, and this is done extremely fast. And finally, you see the output coming on your screen. This is the only part that you get to see after running your program, and it happens so fast that you see the output instantly most of the time. So let's quickly summarize everything that works together to make your C++ program run. It all starts with G++. Think of G++ as the manager. It doesn't do the work itself, but it calls everyone in the right order that is needed. First is the preprocessor that cleans the code. It expands the hash includes that you include in your program. It handles the macros, removes the comments. It does all these things, the text processing. And next comes the compiler that translates your C++ code into assembly language and checks for errors. Then the assembler converts that assembly code into machine code stored as object files. After that, the linker combines your object files with the required libraries to create an executable. When you run the program, the loader loads the executable into the memory and prepares it to run. The CPU then executes the machine instructions one step at a time and very fast. And finally, you see the output on your screen. So when your program runs, all these members work one after the other to give you the output that you desire.